Hey everybody, this is Larry. This is day 18 of the Leetcode Daily December Challenge. Hit the like button, hit the subscribe button, join me in Discord. Let me know what you think about today's problem. So I do explain and solve these live, so if it's a little bit slow, let me know or fast forward. I usually go for my thought process and not just the solution, so your mileage may vary. Okay, so today's problem is increasing triplet subsequence. Okay. So okay, n is 10 to the 5th. I think there are a couple of naive solutions, and the really naive is n cubed, where you go ij for I for j for k, right? It's probably a little bit easier to do an n square just by for just like two loops, and then you kind of check where in O of 1 whether there's a number that, or like the biggest number that's to the right or something like that. And you could, there are some linear time algorithms for sure, though try maybe not know one complexity, because basically the idea that I had was that okay, you're just basically trying to get the min. So for each number, you're trying to get the min to all the numbers to the left or previous, and trying to get the max of all the numbers to the right. And if the current number is bigger than the min and smaller than the max, then you have, then you can do it in linear time, and that is very straightforward. Kind of, well, the prefix part is easy because you could just do it as you build, but on the suffix part, you either use, you either use, you can maybe use some sort of like mono stack or something like that, but you could also just have a suffix array of the running max, which will be monotonic, obviously. So, which is, another way of doing mono stack. Of course, that's going to be linear time, but that's going to be linear space. Don't know if I should go over that one a little bit more, but okay, right? Let me go over that very briefly, and then we'll go over the one with O1 complexity. I think I have an idea about O1 complexity. I do want to go over it because I feel like that is a pattern that comes up in other problems or other similar problems, and it's a good way to kind of think about it, right? So there are two techniques that we can think about to solve this in linear time and linear space. You can have it for loop, so for x in nums, and then min to the left, say. I mean, my variable names are a little bit longer just for explanation reasons, explanatory reasons. So as you go to, min of x, well, maybe x and then the current min, right? To the left, right? So we have to start this off by some like infinity. That's fine, right? And then we have to, of course, we only update that afterwards, but then, max to the right is equal to some stuff, so we'll put that on later as well. So then basically our check is if min to the left is between, does it have to be strictly increasing? It has to be strictly increasing, so I just have to check the signs. Max to the right, then we return true. Otherwise we return false. And of course, we update the min, which is easy as we do a rolling sum, and then we can update, or we can set the max by just having a suffix max. So let's have a suffix max is equal to an array of it could be negative infinity. So let's just do negative infinity or negative really big number times n plus 1. I always do n plus 1. Yeah, n is equal to the length of nums, of course. Put it in top, and then now we go backwards. I like to write in a while loop, so n index is equal to n minus 1, while index is greater than 0, index minus 1. So, and then suffix of max is just equal to, or suffix of max of index is just equal to suffix of max of index plus 1, max of this, and the num sub index, right? So I hope I don't have to explain this part. Let me know if I do, but but I would also recommend just looking into prefix sum, prefix and suffix sum, and all those things. This is basically that idea of basically just rolling a for loop as well, right? Basically, you're looking at, I'll do a quick example real quick. But basically, what this loop does is that, it goes for the last element, and actually there's an extra element that's negative infinity. And then look at the last element, it looks at, is this the max? Yes, then let's put it in there. And then looks at the 4 and goes, is this the max? No, so let's take the previous max. And so forth. So then now we have a lookup table of things to the right and the max of that number. And actually this is a terrible example, to be honest, because this is all 6. But that means that at every point to the right, so the query that you want to answer is that for this number to the right, what is the max number? And that's a 6. And you can do this all one time if you build this out in all of n time. And then so here is just and actually we could just put this up front because it's the same anyway. Suffix max of index, right? And of course you have to set index here. Enumerate just adds it to the index. So something like that. We're gonna run the code real quick. So this looks good. I'm not going to submit it yet because I want to do an optimization. And this is kind of an optimization I like to talk about because it does come up from time to time. And you may hear the term monostack or monotonically. I guess in this case, it is decreasing stack, right? And basically the idea is that you build this array in a good way. This takes all of n times to build, and there's really no way about it because you have to look at everything. But you can actually convert this into a stack because by noting that, and this is not a great example, but actually let's use this one let's just not only use this one. I'm going to put it in the middle, maybe. No, take out the 6. No, let's just put it in the end, and then put 6 here, and then here it's going to be all 6. So then now when we generate the array, it's going to be negative infinity 1 2. I'm running it backwards, so that's kind of silly, but so it's just going to be 6 6 6 6 5 4 3 2 1, right? Oops. And as you can tell, it is monotonically decreasing, and so if you're really slick about it, you could convert this into a stack, and going from right to left, and that would save you some space. But and I think in this example, and let's say you have another 5 here, or another 7. I don't know. Like this is always going to be monotonically increasing, and you may skip some numbers if there's a 5 here, for example. Then you have 5 5 here instead. But anyway, my point is that this is a good pattern to notice because it comes up in different problems. In this problem, it actually doesn't save you that much. I mean, in theory, you could say that it saves you a little bit extra space depending on the longest decreasing subsequence or something like that from the back. But it's not going to, it's still going to be linear time. It's still going to be linear space in the worst case, in the case of everything being decreasing, right? But I like to point it out because it is a pattern that comes up from time to time. And knowing these patterns will allow you to simplify things for, different constructive reasons, right? Okay, cool. So that is the linear time, linear space one. Let's think about the O of 1 space, right? So I actually don't like the O of 1 version of this that much. I mean, it's cool, but I don't like thinking about it in that term. What I would like actually to think about is actually dynamic programming. And if you saw this coming from the beginning, let me know, because I think what I remember is the explanations that on this type of problem is that I always bring up Cadaine's algorithm, which is that when you look at people's solution and they take away the they take away the dynamic programming aspect. It makes it harder to understand for me, or from my angle, I think I find it harder to understand because some of the logic is just like too magic-y, it's just like, oh, this is a thing, and yeah, if you want the algorithm, it's true and you're able to prove it, but for me, true learning is about reproducing it and solving a new problem using it and stuff like that, right? And this is not related to Cadaine's algorithm except for in a sense that of the space reduction part of dynamic programming, which we'll go over in a second. So the way that I would think about it is thinking about, well, this is actually similar to a problem that you may have faced before, the longest increasing subsequence, right? So basically, I'm not going to go that deeply into longest increasing subsequence because that is a long explanation as well. But so I am recording these explanations live and trying to think about the best way to explain it. So my apologies if it's a little bit rough. But yeah, for the longest increasing subsequence, there's the n-square algorithm where, very naively you have, let's just say LIS3 maybe for naming is hard, or even IS3, right? We're increasing subsequence of 3. You have an index, you have a count, and the thing here is, and this is kind of involved, but you have the index and a count are the states, where index is the index of the nums, and count is you go to the count of numbers to the left of index that are smaller than index, something like that, right? And in that case, your algorithm will look roughly like this. If count is equal to 3, then return true because that means that you're able to get there. Otherwise, you have a for loop that goes for, I don't know, next index in range sub n, starting from index plus 1 maybe. And then you have something like if num sub index is strictly less than num sub next index, let's have possible is equal to false, then possible is equal or equal to is 3 of next index count plus 1, right? Something like that. And then return possible at the end. So I'm not going to even run it because this is going to be way too slow. But I just want to illustrate this because this is n square, right? So this is n square implementation of the longest increasing subsequence if you only need 3 of them. Again, of course, n is 10 to the 5th, so that's going to be way too big. N squared is going to be way too slow. Even though the states, they're only O of n states because count is only going to go up to 3 and index goes from 0 to n. But anyway, so now we're gonna convert this to top down, and the way that you would do that is something like this. For next index in range sub index plus 1 of n, dp maybe something like if num sub index is, well, in this case the next index is a smaller one, so that's actually terrible. Maybe name a previous index, Larry. Okay, fine. No, this is still next index, but I'm doing it, I like to do it the other way when I do this. So actually we should go from 0 to index, so that if num sub index is greater than num sub previous index, then possible of index is I forgot about the 3 side. Well, you could do it in a number of ways. So then you could actually just do like something like the impact is you go to the max of dp sub index, dp of previous index plus 1, and then in this case we would just return dp of if index or if any of the index for index in range sub n, something like this, right? So now we check whether any dp has a count of higher than 3. So, and that's one way to do it. Another way to do it is to notice that it has 3 variables, right? So we can rewrite this to or like the count goes up to 3. So we can rewrite this to add it to third dimension to kind of fill out that Boolean map instead of having this. mostly equivalent. But the reason why I want to focus on this part is that, yeah, so there are a couple of ways to do it with dynamic programming. The reason why I want to focus on this part is that longest increasing subsequence, if you do remember, has an n log n reduction. That reduction is actually kind of tricky to prove and understand, but the short idea behind that is that okay, so you basically how do I want to explain it? But I would definitely implore you to kind of try to understand that explanation because it is kind of hard. I'm going to go over a little bit, but probably not in depth for you to like really understand it if you haven't seen it before. But the idea is that, okay, right? And it's kind of a tricky idea, so that's why I don't know if I'm well equipped right now prepared to explain this. But basically the idea is that, okay, right, you look at the longest in the longest subsequence, instead of storing the dynamic programming on index, we store it based on the length of the longest increasing subsequence, right? And of course that's going to be O of n space because the longest it could be is just n elements, right? So the thing is that if you take any longest, let me take an example here, is that we can construct an array, in n squared time, say. I mean, and there are ways to obviously change this to n log n. That's the basis of dynamic programming. But the idea here is that, okay, for each number that comes in, we keep a storage of the smallest number that is the last number of a length of a longest increasing subsequence of length I. So okay, so let's say we have an array called longest length. Let's just set it to start with negative infinity. Oops. Oh, I don't have infinity set up. Okay, negative infinity times n, right? N plus 1, I guess, actually. And from here, let's define this. Let me write it out and define it. Longest length. Maybe I call it the. Let me try to think about naming this. But okay, fine. Let's just stick with this name. Longest length sub I contains is equal to the smallest number that the smallest number of that ends a chain or ends a increasing subsequence of length I, something like that. And I'm gonna, and that only contains the smallest last number, but I'm going to show the list just to show, right? So for example, in the beginning, this is equal to just nothing, right? Negative infinity, right? So negative infinity. This is pseudocode anyway. So, and then now we process the 2 right here. So 2, and we're going to just do an algorithm. So then now, what's the longest length of 0? Well, it doesn't change because it doesn't do anything. So then here, the longest, so this is actually undefined technically, I suppose, actually. But longest of length 1. So up to this point, what is the increasing subsequence of length 1? What is the smallest number? The smallest path, right? And right now it's just 2, and all the other ones going to be undefined. And then now we're going to go to 1, and well, here the smallest number that could be ending at a path 1 is going to be 1, right? So now we replace the 2 with 1, and we would actually also replace this, but this is still undefined because there isn't one that exists. And then now we're going to do 5. 5 gets interesting, right? Where's the longest length of 1? Well, 1 is still going to be the answer. So then now we could take this, we could use this to build on the longest of 2. and now we have 1, 5, right? This is the longest. This is the subsequence of length 2 at up to this point. Oh, I have to update this to 0.5, and then we do it for 0. Well, for 0, now we go for the for loop, and this is actually 0. This is smaller than that, so this is going to be updated to 0. I'm going to add more numbers in the end just to kind of show the longest increasing portion, right? And then now we do the for. Well, the for, now we can either take, and this is where the dynamic programming type of mindset gets in, is that, okay, so the new, longest of 1, it's not going to be smaller than that, so that's fine. But the longest length of 2 can either be the current longest length of 2, which is just 1, 5, say, or the longest length of 1 plus concatenated by 4, which is equal to 0, 4, right? And in this case, we do this comparison between 1, 5 and 0, 4. And 0, 4 is, smaller because we only care about the last element. And I guess by tiebreakers, you could go up the list, but it shouldn't matter too much, at least in this problem, because you don't need to minimize anyway. You only need to get the smallest one. So then now we update this to 0, 4, right? And I guess technically before that, I guess you have to do it in an order that makes sense. Otherwise, like in theory, you could add a longest length of 3, but it's still undefined because if your number is 4, you cannot add it to the longest length of 2, and you know that because if you do it in the right order, well, then invariant is that if the last number, the longest length sub 2 is 5, there's no possible subsequence of length 2 that contains smaller than a 5 as the last digit, right? So then anyway, now we update to 0, 4 and so forth, and then now update to 6, nope, and then this is 0, 4, 6, right? And then look at 7. Well, I mean, there's going to be a longest length of 4, I'm just going to that part just to kind of keep it short. And then now we see the 2, it becomes interesting again. This is no good, no bueno, because 2 over 4 is no good. So, but this one, longest length of 2 is just longest length of 1 plus the 2. So then now we can update it to 02. And then 8 at the very end, we update all the bigger ones. And then let's just fit in a 5. If we have a 5, then actually, even if we have a 6, then actually the longest length of 3 gets updated because longest length of 2 plus the sequence of 5, this becomes 0, 2, 5, say, right? Oops. And that's pretty much the idea. Okay, so that's the idea of the longest increasing subsequence in n log n. Or, well, that's an alternative version of n squared because, you see me do this n squared. But the thing to notice about this sequence is that if you only look at the last number, and now we move until except for the last number, well, the last number is actually always going to be increasing, right? Because, by contradiction or something like that, where if this number is bigger than this number, then well, there's just a contradiction because then either this should be 5. Let's go back to the more digit ones, right? Like if this number is 06, for example, right? That means that there's a contradiction because for the length of 3, there's always, you could take a subset of this and replace it with, a sequence of 2, right? So by that logic, this is always going to be in increasing order. And because it is in an increasing order, you can binary search to figure out what's the longest length that you can do to the longest length you can do to alter it, right? And then change that number going forward. Yeah, so that's the n log n explanation of the longest increasing subsequence. Kind of, I hand waved a little bit, but that's kind of the idea behind it, right? But in this case, as we talked about, this is actually just an increasing subsequence of length 3, and we have to check whether it exists. So the short answer is we just use the same algorithm, except for that we keep only the first 3 elements, and we don't even have to care about the log n part. We don't, or log k or log n or whatever, because this is a constant, right? We just care about the first 3 triplets. So now we're going to write it again, right? Now we're going to write actual code. Yeah, and here we can just say this is 3. Let's say this is 4 because this is 3 plus 1. Just for so that I don't return early, so that you could see the example a little bit more. So yeah, so now for no, so what I want to do is a little bit different. No, this is fine. I mean, we could do a little bit more illustrative, but yeah, but now basically we just implement what I said, which is that for let's say x in nums, and then now we go through the lengths. So for length in range sub 4 to, this is a weird way to look at it in Python, but basically it just goes from 4 to 0, right? So basically what this does is implement what we mentioned earlier. So if longest of length minus 1 is less than x. No, I mean, it's true, but we actually have to be careful about using just negative infinity in this case, because technically it's more undefined. But yeah, maybe I should just make it more explicitly undefined. Maybe that's a little bit better, so that we have an extra variable about saying it not exists. But basically now we go if longest length of length minus 1 is not none, meaning that there is a value, and this value is smaller than the current number. Let's actually name it current, because I use x too much, gets me in trouble. Then now basically what we're doing is, okay, we're saying there is a subsequence of length minus 1, and that the last number is going to be smaller than the current number. Then actually now we can create a new increasing subsequence of length, right? So longest of length sub length is equal to the min of the current number, because this is the last number, and just the previous length. So like, you know, if it is already small enough, then you don't have to update it, and that's pretty much it. So now at the very end, and I know that you could actually you could do an early return or something like that, but I just want to show at the very end, we just do return longest length of 3, and checking that it is not none, right? Let's run the code real quick, because maybe I have typos, hopefully not. Ooh, false for false. Well, it's false because everything is none. So we have to set length sub 0 is equal to negative infinity. This is a little bit awkward, but oh yeah, and we don't update 0, so actually we should just go from 4 to 1. So there are 2 minor errors, hopefully. Let's run them real quick. Oh, none type and int. I thought we checked that it is not none. Line 18. Oh, because if this is none, then yeah, okay, fine. So if the longest, so if the current is none, then we just take it. Otherwise, we take the min. Okay. Whoopsie daisies. Coding is hard. Ooh, index out of range. What? Oh, this should be 3, of course. I don't know why I started at 4. So this should be 3 to 1. Man, off by ones. My brain is a little bit juicy today. But yeah, so that looks good. Let's give it a good submit, and hopefully that's right. If not, it'll be a little bit sad. Okay, cool. So what is the complexity, right? Well, it's going to be linear time, because we look at each, for each number that is in nums, we do a for loop, sure, but it only has you know, it's a constant amount of iterations in the for loop, so it does a constant amount of operations, especially inside. So this is going to be of n time. In terms of space, well, we only create four like array of size 4, so it's going to be constant space, and that's pretty much it. I know this is a very long video, and hope you learned something from it, because there are a couple of techniques here in general, but it's kind of a cool problem, and I dig it. And it is something that once if you remember the trick, then it is much easier. But for me, it is about kind of knowing why like this works. It's kind of important as well. And of course, once you're more familiar with it, then you're actually able to do this for, like this just becomes longer as increasing subsequence of size, whatever. So yeah. And you could do a binary search here, but that's fine. Cool. That's all I have for this problem. Let me know what you think. This is a long video, but I hope for a good reason. So yeah, definitely watch at your own pace, and I'll see you later. Bye bye.